In this video, we're going to work a bunch of problems from Chapter 2 of the textbook, different types of problems. So Chapter 2 was titled Atoms, Molecules, and Ions. In one of the previous videos, we flipped through Chapter 2, and so we're going to work a bunch of problems on all of those topics. Some of those topics also have their own separate dedicated videos. So before you watch this video, go watch all of those videos in the playlist before this video. After you've watched those videos, come here, and then for each problem, pause it and try and answer it on your own, then watch the solution. And by the end of this video, all of the knowledge of Chapter 2 will be sort of cemented in your head, in your brain. Okay, let's get started. Define the following terms: alpha particle, beta particle, gamma ray, X-ray. Okay, so these first three, those are associated with radioactivity, radioactive decay, from the decaying of the nucleus, the spontaneous, natural decay of the nucleus. These are all very high energy, these three. An alpha particle is a positively charged particle. It's two protons and two neutrons in a cluster, no electrons. So it's sometimes written like this. So helium, because it's got two protons, and then mass number 4, and then with like a 2+ to indicate there's no electrons. Okay, a beta particle is a negatively charged particle. It's an electron. It comes from the nucleus, but it's like a neutron breaks down into a proton or something like that, and then it also emits an electron. A gamma ray is just an electromagnetic wave. If you look at the electromagnetic spectrum, it's the highest energy electromagnetic wave. And again, it comes from radioactive decay, the breakdown of the nucleus. That's why it's so high energy. It's coming from the nucleus. An X-ray is an electromagnetic wave, not as high energy as the gamma ray. X-rays come from just a larger amount of acceleration or deceleration of electrons, so larger than like visible light. Visible light, it's coming from an electron jumping from one energy state in an atom to another. X-rays, it's even more acceleration than that. Okay, compare the properties of the following: alpha particles, cathode rays, protons, neutrons, electrons. All right, alpha particles they're particles, not rays, positively charged. So they're repelled by a positively charged plate or attracted to a negatively charged plate. Cathode rays, I guess you could say they're rays because they have, it's not a particle, but I'm kind of confused by this because I thought cathode rays contained electrons. That's why, since cathode rays they're negatively charged for sure, and since they're deflected away from a negatively charged plate, that's how they discovered the electron. I've never heard of an electromagnetic wave being charged, so I don't know. Cathode rays were that invisible beam that came off of having two charged plates, and then since they're so highly charged, this ray results from the plates, and it's deflected away from a negatively charged plate, which I thought it contained electrons in the ray. So I'm not exactly sure. That's something you can look up. Okay, protons are particles. They are attracted to a negatively charged plate. Neutrons are particles. They aren't deflected by any charged plate. And electrons are particles, and they're deflected away from a negatively charged plate and towards a positively charged plate. Describe the contributions of the following scientists to our knowledge of atomic structure. J.J. Thomson he discovered the charge to mass ratio of the electron. Millikan was the Millikan oil drop experiment. He discovered the charge of the electron. And so since you had the charge to mass ratio and the charge, you could determine the mass of the electron. Ernest Rutherford discovered the nucleus, and James Chadwick discovered the neutron. Describe the experimental basis for believing that the nucleus occupies a very small fraction of the volume of the atom. So yeah, this is how Rutherford discovered the nucleus. He was shooting alpha particles through thin foils of metal, and the vast majority of the time, the alpha particles weren't deflected at all, which meant that the atom was empty space. But then the alpha particles sometimes would get deflected an extreme amount, like almost in the reverse direction. So alpha particles are so high energy. They're, high energy. It's like that's coming from, radioactive decay, right? That's what nuclear power plants operate on, the nuclear bomb. And these alpha particles were getting completely deflected in the opposite, sometimes in the opposite direction. So the nucleus had to be extremely dense and extremely small at the same time, because because most of the vast majority of the time the alpha particles weren't getting deflected at all. The diameter of a helium atom is about 1 × 10⁻² picometers. Suppose that we could line up helium atoms side by side in contact with one another. Approximately how many atoms would it take to make the distance from end to end 1 centimeter? Okay, so what we do is we say we start with what we know. We've got 1 centimeter. Okay, 1 centimeter. Now, we need to convert to picometers. So let's first convert to meters. So we've got what? You've got 10 to the second, so 100 centimeters, right? Centi, in 1 meter. All right. Now, you've got 10 to the 12th picometers in 1 meter. Okay. So now we're in picometers. That's what we want. So what can we do? We can say that 1 helium atom, right? Its diameter, so like 1 helium atom, its size or its diameter is 1 × 10 to the second picometers, which is just 10 to the second. So 10 to the second picometers. And so there you go. Now we've gone from 1 centimeter to the number of helium atoms, to the count of helium atoms. So we can say what? This is 10 to the second. All right, so this goes to 10. That cancels. This goes to 8. That cancels. So 1 × 10 to the 8. So 10 to the 8 helium atoms. What is the mass number of an iron atom that has 28 neutrons? Okay, iron has 26 protons. So if it has 28 neutrons, then the mass number is the number of protons plus the number of neutrons. 8 plus 6 is 14. So 54 is the mass number. All right, calculate the number of neutrons in 239 Pu. I guess that's plutonium. Yeah, plutonium. All right, so it has 94 protons. So it's got 94 protons. That's the mass number. So the number of neutrons is just 239 minus 94. 9 minus 4 is 5. This is 5. 155 neutrons in 239 plutonium. Wait, no. This is a 4. 13 minus 9 is 4. 145 neutrons in 239 plutonium. Write the appropriate symbol for each of the following isotopes. Okay, Z is atomic number, and A is mass number. So what you do here is the atomic number defines the element. So you just go look up the element based on the atomic number. It doesn't matter what A is. Z defines the element. So 11 is sodium. All right, so for part A, we're going to have 11 like that, and then we can just put A. That's the this is the mass number. Okay? And then, so for part B, what element has 28 protons? 28, nickel. So we've got 28, and then A is just put A. It's not say if it gave us the number of neutrons, we'd have to do some algebra to get the mass number, but it just gives us the mass number. So just put the mass number. Okay, elements whose names end with "ium" are usually metals. Sodium is one example. Identify a non-metal whose name also ends with "ium." All right, that's interesting. Okay, right. Sodium is a metal. What about a non-metal? Okay, where are the non-metals? All in this region. That's the non-metals. Everything else is metals. Okay, these are transition metals. So let's see if we can look at the true non-metals and find an "ium." Helium, there we go. Selenium. All right, helium and selenium. And then I guess tellurium it's a transition metal. So no, these are metalloids. I'm sorry, not these are all transition metals. When you're going from the transition metals to the non-metals, you have the metalloids. Okay, so of the metalloids, these are metalloids in this dark green here, this like forest green or whatever it is, army green. Tellurium, there's an "ium." Germanium, so those are some metalloids. All right, interesting. All right, group the following elements in pairs that you would expect to show similar chemical properties. So, well, we can let's do this. So you can see here are the elements. And when you look at the periodic table, similar chemical and even physical properties, that's based on the vertical columns, the family. That's called families, or groups, or groups, right? This is group 1, group 2. That's called a family or a group. Horizontal rows are called periods. But if we want to look for elements that's the most likelihood that they've got similar chemical and physical properties, we want to look at the groups. So, okay. All right, potassium. Do we have any other in group 1? Potassium and sodium. Okay, those will definitely be similar. Okay, let's see. We have chlorine and what else? Chlorine and fluorine. All right. And then what about phosphorus and nitrogen? Are those in the same family? Yeah, phosphorus and nitrogen. So that's what they're going for. They want you to just remember the idea that the groups result in similar physical and chemical properties of the elements. And why exactly that is, well, there's going to be a whole separate chapter on the periodic table later in the playlist. What are allotropes? Give an example. How are allotropes different from isotopes? Allotropes are two distinct forms of the same element. The best example is diamond and graphite. Both are the element carbon. They're made of the exact same atoms. So naturally occurring carbon is going to have, a certain abundance of the different isotopes of carbon, but carbon and graphite is the exact same composition as far as it's carbon, but it's just two different forms of carbon. One's diamond, one's graphite, right? Isotopes are, you're talking about not the element, not a substance, but the atom itself. Carbon atoms that have different mass numbers, different numbers of neutrons, right? It has to have the same number of protons because then it wouldn't be carbon, but different numbers of neutrons. That's what an isotope is. Give an example of each of the following: a monoatomic cation, a monoatomic anion, a polyatomic cation, a polyatomic anion. Monoatomic, that means just one atom. One atom. So Na plus. Okay, a monoatomic anion. I mean, we can come to the periodic table. Okay, it doesn't mean that it has to have a charge of 1. So, like, you could say F minus or even O2 minus. These are both monoatomic anions. Okay, a polyatomic cation, not diatomic, polyatomic. So more than 2. Now, also it's confusing because, here's a polyatomic cation. NH4 plus. Right? There's only two different, there's only nitrogen and hydrogen. It's only 2 types of atoms. No, but it's multiple, more than 2 atoms, like more than 2 total atoms. You have 5 total atoms here. Okay. Now, a polyatomic anion, you wouldn't say like, that's diatomic. Okay. You could say that's a polyatomic anion. Which of the following diagrams represent diatomic molecules? Polyatomic molecules, molecules that are not compounds, molecules that are compounds, or an elemental form of the substance. Okay, so let's see. Diatomic molecules, more than, or just 2 atoms. It doesn't matter if it's the same atom or not. Okay, these have more than 2 atoms, so this is a diatomic molecule. Polyatomic molecules, more than 2 atoms. Right? This is 3 of the same atom. That's still more than 2 atoms. Same here. Okay? Molecules that are not compounds. Okay? What does that mean? This is an element. This is an element, not a compound. These are compounds, right? It's like H2, the molecule H2. That's the element hydrogen. O2. If you have just pure O2 in a container, in a pressure vessel, that's the element oxygen. That's not a compound. Okay, molecules that are compounds. It's a combination of more than one type of atom. Like water, that's a compound. Hydrogen chloride, let's say, that's a compound. Or an elemental form of the substance. An elemental form of the substance. This. It's not a compound, it's an element. This is not a compound, it's an elemental form of the substance. Give the number of protons and electrons in each of the following common ions. Okay, so for each of these, we just look up its atomic number. That's the number of protons. Right, so we can, let's do this. Okay, so let's just, for the protons, let's just go look up the atomic number. Na is 11. Okay, so this is going to be the protons. Calcium, 20. Aluminum, 13. Iron, 26. Iodine, 53. Fluorine, 9. Sulfur, 16. Oxygen, 8. Nitrogen, 7. Okay, now the number of electrons. So we'll put this E here. And you just like, okay, Na plus, it has a positive charge. So it's going to have 10 electrons, right? Because it's got one more proton than electron. It's got a positive charge. Calcium, it's going to have 18 electrons. Calcium 2 plus. Al3 plus, it's going to have 10 electrons. Fe2 plus, it's going to have 24 electrons. I minus, it's going to have what? 54 electrons. It's got one more proton than it has, or one more electron than it has protons because it's negatively charged. F minus, 10 electrons. S2 minus, 18 electrons. O2 minus, 10 electrons. N3 minus, 10 electrons. Okay? Define molecular formula and empirical formula. What are the similarities and differences between the empirical formula and molecular formula of a compound? Okay, the molecular formula it's the literal, like if you have a substance, it's a molecular substance. It's made up of molecules like water. For each distinct molecule, you put the number, like the number of atoms. So like the best example of this is like C2H6. If you've got a container of C2H6, well, you're saying when you write this is the molecular formula. When you write this, you're saying that each distinct molecule has 2 carbons and 6 hydrogens. Okay. Now the empirical formula is just giving you the ratio of atoms in a substance. Like the empirical formula for this, for C2H6, if you had a vat of C2H6, would be CH3. Why is that? Because in C2H6, you've got 1 part carbon to every 3 parts hydrogen. 1 part carbon to 3 parts hydrogen, right? It doesn't matter. It has nothing to do with the molecules. You're just talking about, in general, how much carbon compared to hydrogen is there in this substance. It's 1 to 3. But this is not this is the empirical formula, but doesn't mean you have methane, right? Methane is CH3. So methane, the molecular formula for methane is CH3. These are 2 different substances, C2H6 and CH3, but both have the same empirical formula because both are 1 part carbon to 3 parts hydrogen. You see? Okay, write the formulas for the following ionic compounds. Sodium oxide, irons. Okay, so, all right. Sodium oxide. What is the ion for sodium and oxygen? If we come here, sodium is going to be a +1. Oxygen is going to be a 2-. So Na plus O2-. We just do this process, right? If it's an ionic compound, you're going to get Na2O. Iron sulfide containing the Fe2 plus ion. Okay, so it gives us, we're going to have Fe2 plus, right? They need to tell us that because it's different from like sodium and oxygen. You could have multiple different types of cations for iron. Those transition metals are like that. Okay, now sulfur is going to be a 2-. Okay, so we bring these down. Wait, no, sorry. You're going to have S2-, like that. Okay, so you bring these down and you get FeS. Right, you don't put Fe2S2. It's not like a molecule. There's no molecule here. Ionic compounds, there's no molecules. You just put the empirical formula. It makes no sense to do Fe2S2. Because there's no distinct units like that. It's just like a big crystal. So you just put the smallest ratio of the integers. Okay. C, cobalt sulfate containing the CO3 plus and the SO4 2- ions. Okay, so I guess cobalt can potentially, see, it's a transition metal. It can form different types of cations. Okay, so just do this, and you get what? You get, so cobalt 2, and then this entire SO4 is going to have a 3. 3 of these SO4s, like that. All right? Barium fluoride. Barium is going to be a Ba2 plus. Okay, and now fluoride, I think, is just a -1. Yeah, -1. Minus. So bring these down. It forms the ionic compound BaF2. Give an example of a case in which 2 molecules have different molecular formulas but the same empirical formula. So yeah, we just talked about that. It was C2H6 and CH3. Both have the exact same empirical formula, but different molecular formulas. What are the empirical formulas of the following compounds? So it's just the empirical formula. You're expressing what is the ratio of one atom to another. So this A, we would say AlBr3, right? It's 1 part aluminum to 3 parts bromine. Okay, Na2S2O4. So we could divide by 2. NaSO2. All right? N2O5, that is the empirical formula. You can't, that's the, just the simplest integers, right? It's 2 parts nitrogen to 5 parts oxygen. You wouldn't say it's 4 parts nitrogen to 10 parts oxygen. That's you would use the simplest integers possible. Okay, and then D, same thing. That's already the empirical formula. 2 parts potassium, 2 parts, I guess that's chromium, to 7 parts oxygen. Right, that's the simplest ratio of the elements. Write the molecular formula of ethanol. The color codes are black is carbon, red oxygen, gray hydrogen. The molecular formula, okay? The molecular formula. So what does that mean? It's for each molecule, you're writing like the number of atoms in a chemical formula, okay? So we say what? There's 2 carbons. The carbons are black, all right? And then typically you're going to have the positive charges on the left of the chemical formula, and then the negative charges on the right. So C2, now let's do H. 1, 2, 3, 4, 5, 6. C2, H6, and then 1 oxygen, O. But really what this is, it's probably more proper, this is an OH group at the end. So you're really saying C2H5, OH, right? Just to specify that it's more of an OH group. You've got this hydrocarbon here, and then attached is an OH group. Okay, but is this is the molecular formula? Is this also the empirical formula? Yes, it is, because you can't express this in a simpler way. Like it's 2 parts carbon to 6 parts hydrogen to 1 part oxygen. You know, in fact, really, you could say like this is the molecular formula, and this is the empirical formula. You wouldn't say this isn't the empirical formula, because this is more showing the molecule. This is the empirical formula. How many parts carbon, how many parts oxygen, how many parts oxygen? That's the empirical formula, the purpose of it. Which of the following compounds are likely to be ionic? Which are likely to be molecular? Okay, we're going to talk about this more in later chapters, but the idea is if there's far away from each other on the periodic table, at least far away, their columns are far apart, then there's going to be more of a tendency to form an ionic compound. Ionic compound means they form 2 ions and then the ions bond. Okay, so SiCl4. Where's silicon here? Here's Cl, and here's Si. See, these are close together, so this is probably going to be molecular. Okay, so molecular. LiF. LiF. That's definitely going to be ionic. BaCl2. Ba and then Cl2. Ionic. They're far apart. B2H6. I don't know. I guess I would say molecular, right? They're far apart, but then not really. Now, I don't think, actually I would say molecular, because hydrogen's not, this is different. Hydrogen's not in this. This isn't like hydrogen's not a metal like this. This isn't really technically part of group 1. So, right, because you see how this is yellow and these are all yellow? It's kind of more in this region. So HB is close together. So molecular. KCl, here's K, here's Cl. So ionic. C2H4, again, that's kind of like the boron, right? It's going to be molecular. What is the difference between inorganic compounds and organic compounds? Yeah, so organic compounds typically contain carbon, but there are some inorganic compounds that don't contain carbon. But in general, you can think about an organic compound. It contains carbon, and it's going to be associated with like biological systems, like life, foods, things in the body. inorganic compounds, it's typically doesn't contain carbon, but there are some compounds that absolutely contain carbon but are classified as inorganic. But in general, you can think about it that way. Explain why the formula HCl can represent two different chemical systems. Yeah, because just HCl, like as it is in a vat or whatever, hydrogen, that's called hydrogen chloride. It's just that's its molecule. That's the name of it as a molecule. HCl is hydrogen chloride. HCl, the molecule. But if it's used as an acid, so if it's dissolved in water, it gives off protons. It's an acid, and in that context, it goes by its name as an acid. So again, if you're for the nomenclature for ionic compounds, you just put the cation, the regular name of the element, and then you take the name of the ion and put an "ide" at the end instead of the regular ending. You do the exact same thing for just molecular compounds as well. For acids, if you have HCl as an acid, you take I guess you could call it the anion. It's not really an anion in a molecule, but you can take the negative particle, and you do this. You say, okay, you do this for any acid. You say hydro, and then it would be chloride, but you replace the "ide" with an "ic." Chloric. Okay, and then that's the acid.